generator, and there is one thing where this part is there. This is called as rotor. Okay, this is the rotor. This is going to rotate. This is going to rotate if you are giving supply, or if you are giving supply and if it rotates, it will be like electrical energy to mechanical energy. That will be a motor. If you are rotating by yourself and if you are generating power, then it is called as generator. Okay, so this is a simple figure of a machine. Yes, same machine can operate as a generator, also as a motor. The same machine can operate both as a generator and motor. Okay, so now for a generator, there is one structure named as turbine in steam power plant where they use coal or nuclear or other fossil fuels. They will heat this thing in order to make the water to get heated up, and through that heating they will be generating steam. That steam will be hitting this turbine. This is called as turbine. You can see clearly that. So there will be some structure which will be like this. Okay, so we'll consider it as a three turbine, three fans of a turbine. When a steam hits here, then this will rotate. So this will be moving in this way. Then continuously this will come here. Then the steam is continuous. So the rotation of this turbine will be continuous. So similar kind of thing is happening here. The steam is going to hit this turbine. Because of this, this turbine is going to rotate. Okay, this turbine is coupled with the generator. This is the generator, you can see, that is coupled with a thing. So this is called as shaft. This is called as shaft. That shaft is coupling this turbine and the generator rotor. So if the turbine rotates, then the generator rotor also rotates. Okay, so here you can see clearly, this is for the wind generation. In this is for the hydropower generation. Here the water is coming from this location. So the water is coming from here. Then here the water is allowed to hit this turbine. This is the turbine part. Okay, each are turbine part. So here the water is allowed to hit this turbine. Because of this water, the energy in the water, this turbine is going to rotate in the anti-clockwise direction. So then what will happen? This is coupled to the shaft. So this is a shaft. This will be coupled to a shaft. That shaft will be connected with the generator. Generator will be here. So that generator rotor will be connected to the shaft. So whenever this turbine rotates, then the generator rotor will rotate. Then we will be generating power. So generally we will be using, most of the time we will be using steam based power generation, because most of our fossil fuels, coal, nuclear and all, are based on steam based power generation. In a hydropower plant we will be using water as a source in order to make this turbine to rotate directly. So the point is, there is a turbine. That turbine is hit by the steam or water. In wind energy, that wind is going to hit this turbine. So in wind energy you would have seen, there are three leaves which will be available here like this. So there it will rotate. This will be coupled here. There the generator will be here in this location. So when the turbine rotates, then the generator which is available on the top of the wind power plant, that will rotate. So because of that, the energy will be generated at the top of this wind plant itself. Okay, so you would have seen wind power plant in uh, in newses and all. So here this is also going to rotate. This is going to rotate based on the wind. Okay, here it is going to rotate based on the water. Here it is going to rotate based on the steam. Here the main fuel is coal. We will be using the coal to be get heated up. Then we will be boiling the water in order to get the steam. So once we get the steam, that steam will be hitting this turbine. So that turbine is coupled to that generator rotor. So whenever the turbine rotates, the generator rotor rotates, then the energy will be produced or power will be produced. So now there is a rotor structure and there is a fixed structure. So this is the rotor structure. This is actually available here. So this is the rotor structure. This is the rotor structure. This we have zoomed it and we have taken it out and we have shown it here. Okay. So here you are having, how we are having is, you are having a cylindrical structure you can consider. In that cylindrical structure, you are going to cut in several parts and you are going to keep wire there. Means this structure will be looking like this now. So this is looking, I mean, so the complete cylindrical structure, they have disconnected this part and they have inserted a conductor here. Inserted one conductor at all the location here. Conductor means it's merely a wire which is going to carry current. Okay, so if you see this in this complete structure, you are going to have a conductor here and you are going to have a conductor here and you are going to have a conductor here and you are going to have a conductor here. So this particular part is cutted. They have cut this particular part and they have inserted a wire here and they have inserted a wire here. They have inserted a wire here and they have inserted a wire here. Okay, so this is going to be the structure. So in this, inside at the center of that, that is going to be a part somewhat like this. Okay, this is a part which is like a hole which is exist on the rotor. So you can project this in 3D. You can project this in 3D. So this is the complete armature part, rotor part. This is also the complete rotor part. So you can see that in between there are conductors. Here they have the conductors and they have, above that they have closed it. Okay, so here they are having a conductor. They have closed it after they inserted the conductor. So you can project this in the 3D. Then there is a shaft which is connecting this terminal, this particular part, this cylindrical part. In the cylindrical part, in the complete cylindrical part, they have cut at the center and they are going to have a shaft here. So whenever this shaft rotates, then this complete cylindrical structure will also rotate. Means this is the shaft. So when this rotates, obviously this part will also rotate. So you can see here that it is mentioned as armature shaft. So when this part is rotated by some means, then the complete cylindrical structure will rotate. Okay. So you can see here that that is given here clearly. The conductor is housed inside, means the conductor is kept inside. Above that you are having some structure. Okay, above this you are having a structure. In between you are having the conductor here. You can see here that the conductor is available here at various places. Then you are having the remaining part. Okay, now, so if the conductor is placed like this, if you see a single conductor, then you can, okay, so this is the complete structure of a machine. In this machine, basically two things are there. One is stator part, one is stator, and second one is rotor. Okay, so already this part, this particular part is going to rotate. This is the rotor part, and there is some part it is already fixed in the machine. So that machine is called as rotor. The rotor, that part is called as stator. The stator is a stationary part. It is not going to rotate. It is fixed. Whereas rotor is the rotating part. It is going to rotate. Okay. So this is about this, both the machine, whether irrespective of whether it is generator or motor, the stator is going to be a fixed part and the rotor is going to be a rotating part. So in rotor, as I said before, in rotor you are going to have the conductors. You can see here that the conductor is given here. In between there is a gap. In that gap they have fixed a conductor. Now that conductor, if you are taking it out, let's say that instead of having 4 kind of conductors like this, let's say that you are having only 2 conductors, one conductor here and another conductor here. Okay, you have cut this part and have inserted the conductor and you have closed that conductor. Okay, you have closed this conductor. Okay, you had cut this part in the cylindrical structure, then inserted the conductor. After you inserted the conductor, you have closed that part. Similarly, here you have cut this cylindrical structure in this manner, then you are inserting the conductor. After you insert the conductor, you are closing it. Okay, why you are closing it is, in the rotating time this conductor should not come out. Just a minute. Sir, hello. Okay, sorry for the disturbance. So am I audible now?
Yes, sir.
Yes, sir.
Yes, sir.
So I was telling, okay, there is some cylindrical structure. In that cylindrical structure, you are going to take a cut, and inside that you are going to insert the conductor. After you insert the conductor, you are going to close that opened part. Okay, so this is one thing, and the second thing is you are going to have a shaft inside at the middle center of this cylindrical structure, and you are going to have the shaft here. This shaft is connected to this part. So generally it will be looking like this. Inside the cylindrical structure it will be looking like this. Then your shaft will be fixed in this gap like this, fixed in this gap like this. So your shaft will be like this. This part is the cut in the cylindrical structure, and this part is the shaft part which is connected to this. So shaft is connected this. So when the shaft is rotating, this is called as key. So this will be coupled with this cylindrical structure. So when this shaft rotates, then the key will be pushing this part. So since it is locked, so this is like this, this is like this. So this is the shaft one, and this is the cylindrical structure one. So since both are coupled properly, when the shaft rotates, this cylindrical structure, which is part of the cylindrical structure, that also will rotate. Okay, so this is the main thing, where if the shaft rotates, so your cylindrical structure will rotate, or in another way, if the cylindrical structure rotates, then your shaft also will rotate. Okay, shaft is the part which is straightened like this. Above that you are having the rotor, means you are having the rotor. So you can say that you are having the rotor. Inside this rotor you are having the shaft. Okay, so whenever the shaft is rotating, your rotor will also be rotating. So that is the basic thing. Now let us go into this machine and let us see how it is going to operate. So here Here, this outer layer, so you can see one conductor here. You can see one conductor here. Regarding this conductor, we will be talking later. This is housed on the stator. This particular winding and this particular winding are wounded on stator. These two windings are wounded on stator. We don't need to bother about it right now. So so you can see very clearly that there are some conductors which is wounded here. So these are wounded on the rotor. Okay, 1, 2, 3. So these conductors are wounded on rotor. So so here there are totally 5 conductors I have mentioned, but behind also there are some conductors. If it is going in some from this part, so the end of that part, this wire should be there somewhere. Okay, so this one particular wire, if you are taking it out and if you are seeing, that will be looking like this conductor, that will be looking like this conductor. Okay, one conductor alone from this, if you are taking out from the rotor part, so I told that there are conductors which is housed over like this one and this one. If you are taking this conductor out, you can see that the conductor will be coming like this. So means that this, if you see in the 3D part, if you see in the 3D, this conductor will be going like this and this conductor will be going like this. Okay, so actually if I'm starting the conductor from here, I have to travel through this path and at the end it will be having a turn like this. Means I am having a single wire. That single wire I am wounding like a rectangular in shape like this. So the conductor will be looking like this. Okay, so it is a single conductor that I am bending it in a rectangular shape. If I bend this in rectangular shape, I will be getting a structure like this that is shown here actually. So with one conductor only, we are going to analyze how the machine is going to work. That's why I am telling about this. So this conductor, which is wounded on the rotor, we are taking only one particular conductor and we are keeping it outside, and we are seeing that as a single conductor. So the conductor starts from here and it is going like this and it is going like this and it is going like this and outside it is coming like this. So you are starting a conductor from here, it will travel this path. So backside there will be a bend like this, then on another side it should come out like this, on another side it should come out like this, and let's say it is coming like this. Okay, so the same conductor which is starting from here, it should travel. So another terminal of the conductor should be coming out to this place. Okay, that is what is happening here. So if I take this as a single conductor and keep it outside, it will be looking like a rectangular in shape. Okay, so now let us analyze. Okay, so let us take a simple north pole and south pole. So from that, let us analyze. So let us take a simple north pole and south pole, and we are keeping the conductor in between. Okay, so this conductor is like this. Now you can see this peak, particular peak. This is looking in the vertical manner, but you can see that there is some conductor which is going to be like this. Okay, that is placed in between the north pole and south pole. So the conductor is going to be like this. So now this is placed over a cylindrical structure. That cylindrical structure is coupled with a shaft. This cylindrical structure is the rotating structure, and that rotating structure is called as a rotor. Okay, so when the shaft rotates, the rotor will rotate, or when the rotor will rotate, the shaft also rotates. Now, you know that the flux lines of a particular magnet will start from North Pole and it will end at South Pole, right? If you are having a magnet, if you are having a North Pole here and South Pole here, the flux lines will start from North Pole and it will be going into the South Pole. Going into the South Pole. So the flux lines you can draw like this. It is coming out of the North Pole and it will be entering the South Pole. So any magnet cannot have a single pole. Means if there is a North Pole, obviously there should be a South Pole associated with that. Similarly, if there is a South Pole, of course there is a North Pole which is associated with that. Whereas in electrical field, there can be a single positive charge and a single negative charge. Whereas in magnetic field, the North Pole cannot be separated from the South Pole. Similarly, the South Pole cannot be separated from the North Pole. So the point is that in magnetic field, you cannot have only individual poles. So you also know that in magnetic field, the flux line will start from North Pole and it will end in South Pole. So flux lines will start in North Pole and it will end in South Pole. So it is going like this. If we see the whole structure, this is a magnetic pole, that is, there is a outside big cylindrical structure. This is the stator part. In this, yeah, there is a layer like this. You are having a North Pole here and you are having a South Pole here. Let's say this is North Pole and this is South Pole. So this is a physical material. Some material is there. This is a material. This is not gap. This is a material. This North Pole and South Pole are fixed on this cylindrical part. Then inside this we are having the rotor. So in this rotor we are having different conductors, that is like this. So there is a gap between the stator and rotor because the rotor should rotate freely. In order to make the rotor to rotate freely, there should be a air gap between this North Pole and this rotor part, and between the South Pole and the rotor part. Okay, just a minute. Yeah. Okay, so that we can see it very clearly from this picture. So in this picture, this is the rotor. This is the rotor part which is going to rotate. This layer, this colored one, and this part, even there is a winding, but we will be talking about this later. This is housed with this stator. This is linked with the stator, and this is linked with the stator. This is linked with the stator, and this is linked with the stator. So here, only one cylindrical structure that is fixed here, and that is having a air gap between this part and this part. So between the stator and rotor, there is some air gap. Now from this rotor, we have taken only two conductors, sorry, only one conductor that we are going to take and analyze. Okay, that is what we are doing now. So now we have taken this conductor. Now North Pole is here and South Pole is here. The flux lines is here. Now from the Faraday's law of electromagnetic induction, whenever there is some rate of change of flux, linking the conductor, then there will be some EMF induced in the circuit. Whenever there is a rate of change of flux linking the conductor, then there will be some EMF induced in the circuit. This is not new to us because in the transformer, when we had discussed, we are having the mutual flux. That mutual flux is a varying flux because we told that the flux will vary according to the current. The current is sinusoidal in nature, so the flux also will change sinusoidal in nature. So this is a flux that is going to change at every instant of time. So the flux will be having the sinusoidal part. So at every instant of time, we will be having a different flux. So the rate of change of flux happens here. So because of that, that rate of change of flux is linking the conductor. What is the conductor here? This is a conductor. This is also a conductor. So this rate of change of flux is going to cut this conductor. So when that rate of change of flux cuts that conductor, that is going to be EMF induced. That's why we had said E is equal to N into dphi by dt. So this is rate of change of flux. This is rate of change of flux, and N is the number of turns available in that particular conductor. So here the number of turns is 10, then this is given by 10. So this particular flux, how much turn it is linking, that is given by this N. So rate of change of flux can link or can cut the stationary conductor, can cut the stationary conductor. The conductor is stationary and the flux is variable. So because of that, there is some EMF induced. That is what we have seen in the transformer. That is what we have seen in the transformer. That is one way of EMF induced. This is called as statically induced EMF. Statically induced static induced EMF or statically induced EMF. This static is depending that the conductor is fixed. The conductor is not moving. There is another way of inducing the EMF. In that part, it is called as dynamic induced EMF or dynamically inducing EMF. Dynamic induced EMF. So in dynamic induced EMF, what we are going to do is we are going to keep the conductor to rotate. The conductor will be rotating and it will be cutting the stationary flux. In the previous case, the flux was changing or rotating. The flux was changing or rotating here, and the conductor was fixed or stationary. Whereas in dynamically induced EMF, where the conductor will rotate and the flux will be stationary. So now from this understanding, you can see that the flux is stationary here because you are having a north pole here and you are having a south pole here. Let's say that you are having a permanent magnet. So in that permanent magnet, you are going to have a north pole here and you are going to get a south pole here. From that, from north pole to south pole, flux will be there. Okay. Now, now what we are going to do, already we told that this wire is housed or wounded on a cylindrical structure. That structure is connected with a shaft. So when this shaft rotates, that cylindrical structure will rotate. Then if the cylindrical structure rotates, this conductor will also rotate. Now in generator, what we are going to do, in generator, we are going to convert mechanical energy to electrical energy. When we are rotating this shaft, then cylindrical structure will rotate. If the cylindrical structure rotates, then it will convert mechanical energy to electrical energy. Okay. So how we are going to get the electrical energy is this conductor which is housed on the cylindrical structure. That conductor will see a rate of change of flux because there is a fixed magnetic flux, that is the magnetic field, which is already exist because of the north pole and south pole. Now what is happening, this conductor is going to rotate. When that conductor is going to rotate, that is going to cut the stationary flux which is already existing between the north pole and south pole. So when that cuts the stationary flux, now this conductor will experience rate of change of flux. This conductor will experience rate of change of flux because it is cutting the stationary flux. So when there is some rate of change of flux which is going to be experienced by this particular conductor or wire, there is going to be an EMF induced on that conductor. If the EMF is induced on that conductor, then current will be flow through that particular path if the circuit is closed. Okay, that we will see later. But here what is happening, the rate of change of flux is happening. Because of the rate of change of flux, there is going to be an EMF induced. If there is some EMF induced, then if the circuit is closed, then current will be flow through that path. Okay, so this is about this. Now let us proceed further with that. So you are having a north pole and you are having a south pole. Okay, so you are having the flux lines like this. So this is the cylindrical structure. In this cylindrical structure, you are keeping one conductor here. That is, in 3D structure, if you see on back side, it will be going like this. On at the end of that cylindrical structure, this conductor needs to come back. It will take a turn and it will be coming like this. Then it will be coming like this. Okay, so this is terminal A, let's say, and this is terminal B, let's say. Okay, we'll consider as terminal D. Okay, so only one wire we are having, that we are bending it. So this is A, B, C, D. So this is A, this is B, this is C, and this is D. So this complete conductor is going like this. Now the cylindrical structure can be located like this, or the cylindrical structure can be rotated like this, or conductor is here and conductor is here. Means that this is rotated in the anti-clockwise direction, let's say. So this is A and this is B. So this is the position 1, this is position 2. Okay, so just a minute. So you are having the north pole here and you are having the south pole here. So you are having the cylindrical structure. I'm just drawing it outside. It is here and it is here. So this is conductor A and this is conductor terminal D. So if you project this on the back side, it will be like this. Then so this conductor, let's say it is going like this. This is going to be like this. Now if I draw this conductor, it will be somewhat like this. Okay, let's consider that this is in vertical manner. Means one conductor is on top and another conductor is on bottom. Okay, so just a minute. So in the second position, the rotor is rotated and it is rotated in the anti-clockwise direction. Then your A terminal is here and B terminal is here. So at that time, we are having the north pole here and here we are having the south pole and the conductor is in the horizontal manner like this. Okay, this is the second condition. The third condition is you are having the rotor like this. So again, it has come to the vertical position. So now this is now let us see. This is the North Pole and this is the South Pole. Initially, the rotor is like this, where the conductor is positioned like this. Conductor is on top. One conductor is on top and another conductor is at the bottom. So it is at the vertical position we can consider. Then we can consider this as a horizontal position of the conductor. Okay. So initially, we are having some uh, flux lines. That flux lines is like this. That is going to be start from North Pole and it is going to end at South Pole. Then after 90-degree, if this rotor is rotating in the anti-clockwise direction, then after 90-degree, this would have been rotated in the anti-clockwise direction. Then it will be coming to the horizontal position like this. Then after that, the conductors would be somewhat like this. Then this is for the second thing. Then again, if this rotor is rotating another 90-degree, again this one would have been reversed. So you can see here that the D has come to the top now and A has come to the bottom now. Now this particular thing, the conductor can be looking like this. Here you can see that the AB is at top. Here you can see that the AB is at bottom. Now CD has come to the top. Again, this rotor is going to rotate for another 90-degree. Then once it rotates for another 90-degree, it will come to the this position. Now your D will be here and C will be here. Here A will be here and B will be here. So this conductor, this AB is near to North Pole at this part. Here you can see that the C and D conductor is coming near to the North Pole. Okay. So again, you are rotating this for another 90-degree. If you are rotating this for another 90-degree, we'll be getting a structure like this. So here the conductor A will be coming to the top and conductor D will be coming to the bottom. This will be looking like exactly as the first location. So first and fifth, first is the initial position and fifth is the final position. So once we are starting from the position 1, we are rotating in the anti-clockwise direction. We are moving for 90-degree from 0 to 90-degree between these two. Okay. Then from these two things, we are moving from 90 to 180-degree. Then between these two, we are moving from 180-degree to 270-degree. Then from this, we are moving from 270-degree to 360-degree. So the same cylindrical structure we are seeing that is going to rotate for 360-degree from 0-degree. Let us consider that this is the initial position and the axis is like this. So for this axis of rotation, this is going to rotate in this direction. So this is the 0-degree. So the same position need to come in order to complete 360-degree. So that is going to be taken like 0 to 90, then 90 to 180, then 180 to 270 and 270 to 180. So let us see from the conductor A perspective. Okay. So before coming to that, so let us consider that we are having the north pole here and we are having the south pole here. Okay, now you are having the conductor here, that is A, and you are having the another conductor, that is D here. Now there is a magnetic field already. Okay, there is a magnetic field that is like this already. Now what we are doing, we are going to make this thing to rotate in the anti-clockwise direction. So this conductor will see the rotation in this direction and this conductor will see the rotation in this direction. The direction of the magnetic field is like this. Now from the conductor, the conductor rotation direction, that is given by velocity. The velocity of the conductor is going in this way, whereas the direction of the magnetic field, that is the magnetic flux, that is going to be in this way. So we will be seeing about the expression later. For time being, you just consider that BLV sin theta. EMF induced in the conductor is given by BLV sin theta. B is the magnetic field, L is the length of the conductor. Length in the sense we are having this conductor like this, right? So this between A and B there is a distance, right? So there is a distance, thus you can consider it as a conductor. So this is the length of the conductor. Okay, that is the length of the conductor. V is the velocity of the conductor, and theta is the angle between the magnetic field and the magnetic field and the velocity of the conductor. Now when the velocity of the conductor is like this and the magnetic field of the poles or like magnetic field direction is like this, the angle between these two are zero because both are parallel to each other. Since both are parallel to each other, the angle made by these two things are zero. So at this particular position, the EMF induced is zero. EMF induced is zero. Okay, so actually you can just a minute. You can have the North Pole complete. Just a minute. North Pole here and South Pole here. You can have this here also. Okay. So the point is, you are having a conductor that is going to move in this direction because it is moving in the anti-clockwise direction, and there is a conductor, it is going to move in this direction. This is conductor A and this is conductor D. So the direction of this velocity of the moving conductor is parallel to the magnetic flux which is existing in the system. So because of that, because of the parallel nature, this sin theta, it will be zero because both are parallel. Since theta is zero, that is the angle between B and B, you are going to get zero induced EMF at that particular position. Okay, now this conductor is going to rotate in this direction. So this is the axis. Now let us make this conductor to move. Let us make this conductor to move. So this is the magnetic field. Then let us link these two conductors like this in order to understand. So now let's say that this has been moved and it has come to this position like this. This position A and this is position B. This is the axis of rotation. Now initially it was here. Initially it was here. Now it has moved to this position, right? So now it is moved to this position. Now this is the magnetic field. This is already magnetic field is there. This is the direction of velocity and there is a magnetic field. There is an angle between these two, right? So you are having a conductor now, its velocity is like this. Now you are having a magnetic field, its direction is like this. There is an angle between these two. Similarly, if you are seeing from this conductor point of view, it is going to rotate in this direction and it is going to have a magnetic field like this. Then it is going to having an angle between that. Now for sine theta, you are going to have some value. Because of that, there is some EMF which is going to be induced. Then if you consider the conductor like this, A and B, A and D, this D, then your north pole is here and your south pole is here. Then this conductor A, that is going to rotate in this direction. This conductor D is going to rotate in this direction, which is of this velocity. So the velocity of the direction of rotation of the conductor is going to be like this. Then your flux lines are like this. Now the flux lines are like this. Now the angle between this velocity and the velocity of the conductor is 90 degree. You can see here that it is 90 degree. Because of that, you will be getting sine 90. So the point is that here when the conductor velocity is 90 degree with respect to the magnetic field, their EMF induced will be the peak value. Peak value you will be getting when the conductor velocity is 90 degree with respect to the magnetic flux or magnetic field. Okay, so that is what we are going to see. So this is the basic thing. You are having velocity and the magnetic field both are parallel. EMF induced is equal to 0 when the velocity is having certain inclined angle with the magnetic field. Then you are going to get some value. Either it may be a positive or negative, it is different, but you are going to get some non-zero value when the magnetic field is 90 degree with respect to the magnetic field is 90 degree with respect to the velocity of the conductor. Then the EMF induced will be the peak value. Okay, now let us proceed further. Based on this understanding, we can see that the EMF will be induced. Okay, so now kindly mute yourself. This is the position of the conductor at initial condition. Now since I told that the conductors are like this, then if the conductor is rotating in the anti-clockwise direction, then the magnetic field and the velocity of this, here the positions of A and B is like this. The B is going to rotate like this. Okay, we can consider like this. Okay, so A is here, B is here and A is here. The A is going to rotate in this direction and B is going to rotate in this direction. Okay, sorry, just a minute. So we are seeing from front view, we are seeing the cylindrical structure like this. If we are seeing the cylindrical structure like this, then we will be able to see only two terminals, that is A terminal and D terminal. Then A terminal will be looking like this and D terminal will be looking like this. Then A will be rotating in this direction and D will be rotating in this direction. Now, when, as I told before, here magnetic field is in this direction. The magnetic field and this conductor moving velocity is, the velocity of the conductor is parallel to each other. So at that time, the EMF induced will be 0. At that time, okay, we'll be plotting the graph. The EMF induced will be 0. Okay, now I am moving this cylindrical structure in the anti-clockwise direction. If I move this in the anti-clockwise direction, then what happens? Then at 90 degree, I told that whenever the conductor comes nearer to this poles, then you will be getting the maximum EMF induced. Then when it is at the inclination, we will be getting some value. So between 0 to 90, the value of the EMF induced is going to increase from 0 to some value, and at 90 degree, it is going to have the peak value. So based on this, we can see that the EMF induced will be coming somewhat like this. Okay, I'm considering it as a positive. Why I'm considering it as a positive, that I will be telling later. But you can see that the EMF will be increasing like this. Then at 90 degree, the EMF induced will become maximum. Okay. Then again from 90 to 180 degree, from 90 to 180 degree, at 90 degree, we will be getting the maximum EMF induced. Whereas when it is moving from 90 to 180, we will be getting the reduction in EMF induced. And at 180 degree, we are going to get the EMF induced as 0. Okay, because at 180 degree, the conductors will be again in the vertical position, then that the magnetic field will be in parallel with the velocity of the conductor. So because of that, the EMF will induced will be keep on reducing from maximum to 0, and it will be taking this path like this. Okay, then when the conductor is further rotating, then I will be getting a waveform like this. So this part we'll be seeing the next class, because it is already 10 to, you may be having another class. You join to this class, you join to that class, we'll be seeing this in the next class. Okay, if you have, if you want, hello,
Excuse me, sir.
yes,
So I just want to confirm that as per you said that today we have a quiz at 5:30, right?
yes.
Okay. And so can you please upload the notes?
For second unit, I have uploaded the notes, right?
Yes, sir.
Today test is for the second unit, right?
Yes, sir. But for further units, I'm saying.
No, that I will upload. I will upload. I told Radul to inform me, so I forgot
Yes, sir.
about
I'm
it.
just.
I will upload. I will upload. Don't worry.
Okay, sir.
Thank you.
Okay. Thanks, sir.
If you want to ask anything, you can ask. Else, you can leave the meeting. Thank you for joining.
Thank you, sir.